Howdy, my name is Jesus Ramos, and this is our MXET 300 final project presentation featuring TrashBot Jeff. Our team consists of Von Guillermo, David Lister, Adrian Montero, and myself.
For work distribution, I, Vaughn, implemented the camera in order to create an algorithm for the object detection. I also implemented the object acquisition and delivery algorithm into the main code. David implemented the LiDAR in order to create a proximity algorithm which is used to control the robot for the obstacle avoidance. Adrian designed and programmed the controls for the mechanical arm. He also implemented the Bluetooth interfacing code for the LEGO Mindstorm EV3. Jesus calibrated the objects so that they could be detected by the algorithm. He also created the algorithm for object delivery, and he helped with the debugging and troubleshooting. The goal of the project is that the robot would detect an object and identify if it's recyclable. It would be able to locate the object, then collect it using the claw mechanism. Once the robot's capacity reaches its maximum, the robot would then go to the drop-off location. While the robot is accomplishing its objectives, the robot uses the LiDAR in order to navigate around the environment to avoid any obstacle that may come its way.
We established navigation and obstacle avoidance using the provided LiDAR module, which produces an array of points from every scan. The array was processed to flag any distance within a set perimeter around the robot. If flagged, the point would be checked of its angle and magnitude of its proximity to determine the position of the object relative to the robot. After the processing of all objects, a case structure determines the course of action that the robot should take to avoid the objects.
The color scanning code works by using the images collected by the camera. The algorithm then converts the image into HSV value. Once the image is converted, it is then compared to calibrated HSV values in order to identify whether an object of the same HSV value exists within the frame of the camera. When the camera sees the object within the frame, the robot calculates the wheel speeds required to reach its destination using forward kinematics and inverse kinematics.
The claw and gate on the robot are driven using a LEGO Mindstorm's EV3 brick, which is controlled by the Raspberry Pi via Bluetooth. The code used to raise and lower the arm and gate are programmed on the EV3, which can operate independently from any code running on the Pi. The LEGO Mindstorm's motors are equipped with an encoder which can detect how much power is being drawn. Using this, we can detect when the motor reaches the mechanical limit, whenever the power consumed is lower than what it was set to. This principle is what drives the grabber arm, as well as the gate in the back. To tell the EV3 what to do, a command number from 1 to 4 is sent via Bluetooth using UART. This command is then carried out by the EV3. The main two parts to the robot are the claw and gate. We had already decided that the robot needed to collect and hold the balls until it was ready to return to home. The limitations were that the solution needed to only use one motor for each action and reliably pick up the colored balls. The prototyping process started by building a mechanical proof of concept using LEGO Technique, then modeling it in CAD to 3D print later. Ideally, we would have used this rough CAD design for our final demonstration, but due to time constraints, we were not able to finish and print it. The design you see here is driven using a continuous motion servo motor that is used to drive the main axle, which in turn closes the mechanical claws and lifts the whole structure up and down. The whole thing is 3D print, except for the axles, which are wooden dowels. We ended up having to use the prototype LEGO model since it was faster to make major changes, and we didn't have to reprint a bunch of plastic parts should the design go wrong. The image seen here in the final design is used in the final project. The major additions we made were springs to assist the motor in pulling the ball up, extended fingertips to better guarantee a successful grab, and a plate to direct the ball into the holding spot after being grabbed. The only obstacle was getting the Pi to control the motor. We ended up using the EV3 brick to control all of the motor movements for both the gate and the arm. The EV3 would then receive a Bluetooth signal telling it which action to perform.
The results for our final project were as expected. In the end, the robot performed fairly well, implementing both the obstacle detection and the object tracking codes. We observed that our robot was able to navigate through its environment with no trouble and collect two of each of the color balls and drop them off in a designated location, which we called the drop-off zone.
Here we see our robot's just starting off and then is going for the first color, which it sees is blue. After aligning itself, it will then close the claw and then dump it into its basket. Obstacle avoidance is taking into effect since it does not see anything that it should pick up, but it knows what to avoid and not run into. The narrow camera view does cause some issues because the claw is so prolonged from the chassis, causing some issues with being out of view whenever turning. Potentially having a wider view angle on a camera could also improve this. Once the robot has collected both color balls, it'll then have a process to node go to home, which is identified as pink. Once it has aligned itself to pink, it'll then position itself, then begin to back up, open its gate, drive forward, and effectively drop off both of blue objectives at the point. Next, it is then going to be seeking orange. It already sees one, goes to pick it up, begins to align itself, once aligned, the claw grabs it, returning the claw to initial position, then back into obstacle avoidance. The bot will ignore any other color other than its main objective, which is currently orange, soon to be in view. Robot then collects the second orange ball, resets the claw, and is now in seeking home. Robot has identified home. It's now aligned. It is now seeking green. Closes the claw, dumps the green ball into its basket, returns to obstacle avoidance, to then also simultaneously scan between its objective and knowing where it needs to not run into. Yet again, the angle of the camera is very narrow, so we thought if we were able to potentially add a wider camera, it could actually work a lot better. Robot now sees the green ball, deposits it in its crate, then returns back to navigation. And pardon us from making our own walls because we didn't have enough objects to put in its way to make a fully enclosed room. The robot now sees home. Starts to approach it. The robot now has enough room to align itself properly, whereas the second time it went home, gets itself positioned, backs up, opens its door, and drops off the two green balls.
In conclusion, all of the components of the robot worked well together. We were able to meet our main goals for this project, which were to autonomously locate a ball, move the robot towards the correct ball, collect the ball with the mechanical arm, and deposit the balls in a specific location. With the use of the LiDAR sensor, the camera, and the robotic arm, this robot was able to navigate a course and collect specific objects autonomously. This project was a success and can have many applications in the real world. And that's it. Thanks and gig 'em.